This video will cover section 5.1, the derivative of the natural log function. So you have talked about the natural log function in your past math classes, but now we're going to actually see how natural log works with calculus. And in fact, natural log itself is defined by an integral. So the natural log function is actually the integral from 1 to x of 1 over t dt. So if we look over here at the graph of 1 over t, or 1 over x, in just the first quadrant, because remember the domain of the natural log is greater than 0. So if we look at 1 over t, then what this means is if I take the integral from 1 to 1, then that integral is going to be 0. And we know that the natural log of 1 is 0. So if I continue on now and I say, okay, let's find the area from 1 to 2, and I accumulate that, so that whatever that area is would be the natural log of 2, which we can see would be less than 1. And then if I decide to go backwards, because you can have a value between 0 and 1, but if I go backwards, then if I say, let's say the value at 3/4, then you would have to say the integral from 1 to 3/4, which you would then say was the negative integral from 3/4 to 1. And so we know that the natural log of a value between 0 and 1 would be negative. Okay, so just keep that in mind, and we're not going to get into the specifics as to why. We might look at that in class, but for now, just know that that's what the definition of natural log actually is. So let's look back at some properties of natural log. So maybe some that we've already talked about, that you've seen before. So the domain of natural log is f of x is less than 0 when, oh, I'm sorry, I skipped something. The domain of f of x is x has to be greater than 0. All right, and we know that y is going to be negative when x is between 0 and 1. And we know f of x equals 0 when x equals 1. And we know f of x is greater than 0, positive when x is greater than 1. So just some properties to keep in mind. All right, so if we know that f of x, or the natural log of x, is defined by the integral from 1 over x of 1 over t, and then I find the derivative of that function, so if I take the derivative of this integral, then that's the second fundamental theorem of calculus. So then we would say that's 1 over x times the derivative of x, which is just 1. So the derivative of natural log is 1 over x. So if you think about the graph 1 over x on the function, or on the domain greater than 0, so looking at this graph here, this graph is always above the x-axis. So if this graph represents f prime, and f prime is always above the x-axis, then what do we know about the original function? Well, that tells us that f of x, or natural log, is increasing on the interval x greater than 0. If you think of the graph of natural log, it is constantly increasing. So then now what does the second derivative tell us? So if we take the second derivative, or the derivative of 1 over x, we get negative 1 over x squared, which, if we think about that graph, is always negative. And so if the second derivative is always negative, that means the function is always concave down on its domain greater than 0. And that's what you see with the natural log. It's always increasing and it's always concave down. All right, so then the derivative rule for a natural log function, as we've already seen, is just 1 over x. So the derivative of natural log of x is 1 over x. So what if you're taking the derivative of natural log of some other function? We'll call that u. That would be 1 over u times u prime, or simply u prime over u. So we're going to do some examples with taking and finding the derivative involving natural logs. So looking at example 1, we're going to write the equation of the tangent line. So the equation of a tangent line, we need a point and we need a slope. So they want to know this point at negative 1. So that's going to be, we want to find f of negative 1. And then for the slope, that is going to be f prime of negative 1. All right, so let's go ahead and calculate just f of negative 1. So that's natural log of negative 1 squared plus 4, or the natural log of 5. All right, and so then we also need to find f prime. So just simply f prime of x, that's going to be 1 over x squared plus 4 times the derivative of x squared plus 4, which is 2x, which I'm just going to put in our numerator. Okay, and then if we want to evaluate that at our point -1, that would be -2 over 5, I believe, yes. So now we have our point and our slope, so we're going to write our equation y minus -1 equals -2/5 times x minus, oh, sorry, oops, I put my y value here, y minus natural log of 5 equals -2/5 times x plus 1. There we go. Okay, so there's the equation interchangeable. Our second example here, we just want to differentiate, and as you can see, this is a product rule of x times natural log of x. So the product rule, just to remind ourselves, because it's been a long time, we've been doing a lot of integration, so we need to remember our derivative rules. Derivative of x is 1 times natural log of x minus x times the derivative of natural log of x. So then that gets us the natural log of x minus 1, and that is our answer. I knew something was wrong there. I'm sorry, this is a product rule, so that should be a plus. Okay, all right, so now for just properties of logarithms. This is not calculus here. These are properties that we learned when we first learned logarithms. And in calculus, we mainly focus on the natural log. We'll briefly look at other logarithms of different bases, but it's mostly natural log. So just a few properties that you need to remember. E to the natural log of x is just simply x. The natural log of e to the x is also simply x. Natural log of 1 is 0. Natural log of e is 1. The natural log of a times b, this is an important one. Remember, if you are multiplying something inside the argument, that will end up being the natural log of a plus the natural log of b. Natural log of a divided by b is roughly the same thing. The natural log of a minus the natural log of b. And then the natural log of x to a power, you can bring that power out front as a constant multiple and say that's n times the natural log of x. These are very, very important properties, so make sure if you're rusty on these that you get better on them. All right, so now we're going to apply those rules in taking the derivative. So if I were to take the derivative of this natural log, what you would have to do is 1 over the square root of x squared minus 4 times the derivative, which would be 1/2, blah, 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 blah. I don't want to do that, okay? You can definitely do that, but it's going to take you a long time, and it's going to be gross, and I'd rather use my natural log rule. So instead of doing all of that, what you can do, which will actually make this problem much easier, is use your natural log rules in order to make this problem more simplified. So notice I have not taken the derivative yet. What I'm going to do is I'm going to rewrite this as the natural log of x squared minus 4 to the 1/2 power. And using our natural log rules, that 1/2 can come down in the front. So now instead of that 1/2 making that really gross and taking the derivative, it's now just a constant multiple, and now this is extremely easy to integrate. So we have g prime of x is equal to 1/2 times u prime over u would be 2x over x squared minus 4, which is x over x squared minus 4, and that is a lot simpler than trying to do all of the gross chain rule over on the other side. Okay, so make sure you're looking for those properties of natural logs because they really do come in handy. Okay, so another example where the rules come in handy is I don't want to do 1 over this value and then times the derivative of that, because then you're going to have to get into quotient rule, and that gets really ugly as well. So instead, before you just dive into this and do chain rule, split this up and use your log rules by saying that's natural log of x minus natural log of x plus 1. And now when you take the derivative, it's ridiculously easy, and that is 1 over x minus 1 over x plus 1, and that is your answer. Okay, so now how about taking the derivative of natural log of the absolute value of x? Now, when I just say a function is natural log of x, and there's no absolute value, it's kind of understood already that the domain is x greater than 0. But now if I have an absolute value of x, you can plug in any value of x that's not 0, including negatives. So what we want to do in order to take the derivative of this is we have to think of this as really two functions. One on the right side of, or the positive side of the axis, and one on the left side. So if we think of this as kind of like a piecewise function, then this would be equal to the natural log of x if x is greater than 0, and the natural log, so if x is negative, we're going to have to take the negative value of that if x is less than 0. So what I'm going to do here is take the derivative of both of these separately and then see what we get. So the natural log of x, we already know, is 1 over x if x is greater than 0. And if we take the natural log of negative x, that'll be 1 over negative x times negative 1, which is just simply going to cross out to be 1 over x. So in fact, if you get if you have the natural log of the absolute value of x, then it actually turns out to be the same thing as if I didn't have the absolute value in the first place. So the natural log of absolute value of x is also just simply 1 over x. Okay? So then if you have the natural log of absolute value of anything, it's simply just going to be u prime over u. Okay, so let's try this with some lovely trig functions. So the natural log of the absolute value of secant of x. So if I was to take the derivative here, we would have u prime over u. So u is secant, so u prime would be secant x tangent x over secant x, which would lead us to just simply tangent of x. Now keep that in mind, because now what if I asked you, because we haven't learned this yet, the integral for tangent of x. We have not been able to do that up until this point because this involves natural log. So the integral of tangent would then be the natural log of the absolute value of secant x. So just keep that in mind. Okay? Alright, so for another one, we'll try secant x plus tangent x inside natural log. So y prime would be u prime over u. U prime would be the derivative of secant, which is secant tangent, plus the derivative of tangent, which is secant squared, all divided by what's inside secant x plus tangent x. So now what you can do is you can factor out a secant x in the numerator. Oh, I'm still getting it wrong. Sorry, guys. That should be secant. And now you can see that when I factor that, there's a factor in the numerator and the factor in the denominator that can cancel out, leaving me just with secant x. So, based on what we did in the first example, therefore, if I ever ask you to integrate secant x dx, then you should be able to tell me that it's the natural log of secant x plus tangent x plus secant. Okay? And both of these, the integral, tangent, and secant, are both in the primary calculus book. These I would like you to be familiar with for this class. Yes, you don't see them quite as much as other trig identities, but I do want you to be familiar with them. All right, so let's move to the next one. All right, so just a slightly different example. We want to differentiate this. Now we see that it is defined by an integral, and we want to take the derivative of this. So that is the second fundamental theorem of calculus. So that means we are not going to do anything to the integrand. We're going to just simply replace t with natural log of x. That's being squared plus 3. Now that whole thing needs to be multiplied now by the derivative of natural log of x, which is 1 over x. And then minus the lower limit, which the derivative will be 0, so we're good here. Then we can simplify that a little bit, so we can say the natural log of x squared plus 3 over x, and that's fine for your final answer. Okay, so another derivative rule that we haven't done in a while is implicit differentiation. So let's try one of those with natural log. So let's take the derivative of natural log of y, so that would be 1 over y times y prime plus 2x equals 2 times y prime. So now if I want to get y by itself, let's say that's, or y prime by itself, let's say that's 1 over y minus 2 equals negative 2x. So then y prime is equal to negative 2x over 1 over y minus 2. Now, if this was a free response answer, this would be an okay way to leave your answer. However, you wanted to completely simplify, which you're going to have to for multiple choice. Let's get practice with simplifying this. So first of all, you have a complex fraction, meaning you have this fraction within a fraction. So I'm going to multiply by y over y in order to get rid of that. So this will be now negative 2xy over 1 minus 2y. And also, this is a more simplified version, but what you would probably see is changing the signs here to make the numerator positive 2xy, and then the denominator would flip, making 2y minus 1. So this really, if this was multiple choice, is what your final answer would look like. Okay, for our last example, there's a new kind of differentiation called logarithmic differentiation. If you look at example 9, for instance, you'll notice that there is no natural log involved. So if you were asked to take the derivative of this function here, you have to, it'd be really nasty quotient rule, and it would be really hard to simplify and all of that good stuff. So what you can do to make it a lot simpler on yourself is take the natural log of both sides. And I know at first that doesn't seem like it would really help, but I want you to see what happens. So notice again, I'm not taking the derivative yet. I'm just simply taking the natural log of both sides. And notice that the function specifies that x cannot equal 2, because if equal 2, then the function would be 0, and natural log of 0 does not exist. So when I take the natural log of both sides, what that allows me to do is to get this nasty quotient over here on the right side simplified down using logarithmic rules. So natural log of y, we're going to keep that alone. And so this will become, that's a quotient rule with exponents. So hopefully you can follow this one step. So the exponent 2 is going to come down, natural log of x minus 2. Since I'm dividing, this will be minus. Square root exponent is 1/2 of natural log of x squared plus 1. So now this is actually something that really will not take a whole lot of work and time to take the derivative of. Now remember, we're still not taking the derivative, and I also have this natural log of y. So what this really is like implicit in a way. So I'm going to take the natural log of y derivative, so that would be 1 over y times y prime. And now over here, when I take the derivative, I have 2 times the derivative of natural log of x minus 2, which is just simply 1 over x minus 2. So I have 2 over x minus 2, minus 1/2 natural log of x squared plus 1. So the d would be 2x over 2 times x squared plus 1. That 2 came from the 1/2, and then those would cancel out. So now I'm almost done, but I want just y prime by itself, and it's being divided by y. So all you have to do is simply multiply this whole thing by y. But when you do that, you want to have everything in terms of x and y. And so what's nice about that is that you just have an equation for y that was given to you at the beginning. So now all I'm going to do is, instead of putting times y, I'm going to put times what y is equal to instead. And I know it still looks really nasty, but at least the actual work to get there
wasn't nasty in itself.
And that is logarithmic differentiation. I'll mention one thing, that the biggest thing that people make a mistake with logarithmic differentiation is they'll do all the natural log stuff, they'll get to this step, and then they'll simply say that that is the answer because they've done all this work, but they haven't reached the derivative yet. So make sure you continue on and